Okay, good afternoon. This is a continuation of the chapter on stacks in Compute 175. So last time we talked about stacks. What are they? We talked about the usefulness of having a stack. So we defined them. We saw examples that we defined the abstract data type for stack. And because we were convinced that they're useful, given the examples that I gave, we started implementing the ADT to create it as a data structure. And to implement it, we chose to use a list. Actually, we used a list from Python where we decided to have the top of the stack at position 0. So at position 0, that's where we push and that's where we pop. So just as a reminder, the stack is a container that can grow and shrink. It's a linear structure, and we typically look at it vertically. So there's a top and there's a bottom. The bottom, you can't touch it, and all the operations happen at the top. That's where we push, means we add something. We pop, we remove something. We can peek, look inside to see what's in at the top. We can also check whether the stack is empty, and we can check the size of the stack. So now that we implemented it, the next step is to implement one of those solutions using a stack for a particular problem, and we'll use our stack that we implemented. Now it's a tool in our toolbox. Why not use it? So the problem that we will start with is the problem of checking parentheses. If the parentheses, the ones that we open, we close, and if they match, a curly bracket with a curly bracket, a square bracket with a square bracket. So I mentioned in the previous lecture that we can use the stack to solve that problem, to verify that an expression with, well, actually a series of these parentheses opening and closing, whether they match or not, and whether they're properly closed. And I said that we can use a stack. We will push to the stack any opening parentheses when we encounter it. So we'll traverse that string, and if we find an opening parentheses, we'll put it in the stack. And then we will pop from the stack as soon as we encounter a closing parentheses. We will pop from the stack, and we compare what we have in the string, the current character, and what we popped from the stack. If they match, then it's fine and we continue. There's a risk that the stack is empty. If the stack is empty, then there's a problem. It means that we are closing something that we never opened. At the end, if everything is matched and fine, we check if there's something still left in the stack. If there's still something in the stack, that means we open something that we didn't close. Okay, so here's the algorithm. This is basically the definition at a high level, how we are exploiting the stack, but this is the algorithm. We are given a parentheses, so that's our input. We are given a string that contains all those parentheses, opening and closing, and from different types. The first thing we do, we will create a stack that we call S. That's our stack. That's an instance of the class that we created last time. So that instance of stack knows how to push, how to pop, how to peek, and how it is empty, and so forth. Then we have a variable that we call balanced. And we'll assume in the beginning that, yeah, my parentheses are balanced. Let's traverse it basically to see the contrary. So if I find any problem, then balance will say false. Okay. For now, we assume we have no problem, so we initialize balance to true. And because I have to traverse my string that has these parentheses will have a counter that we call index, and I'll initialize it to 0. And then I have a loop. While I'm still balanced, my parentheses are balanced, that means that as soon as I find something problematic, my balance will be false, and I'll get out of this loop. So while balanced is true, and my index that I initialized at 0 here, my index is smaller than the size of the parentheses. So that means I haven't traversed the whole parentheses. I will do something. Remember, this algorithm here, it's an algorithm. It's not in a particular language. It's not in Python. It's not in C++. It's just an algorithm close enough to English, but I'm specifying all the different instructions, the sequence of instructions in my algorithm. Okay, so don't confuse it with a programming language. It's not a programming language yet. It can be converted to any programming language later. So anyways, we have back here, we have a loop. What do I do while it is still balanced and my index is smaller than the size of the parentheses? Well, I'll check if the element, so the character at position index of parentheses, is in this set. It's in this string actually. It's a string composed of all the opening parentheses, the normal parentheses, the square parentheses, square bracket, and the curly bracket. If then this current character is one of these opening parentheses, then I will push it where? In S, that instance stack that we created. Okay, it knows push, that's part of its language, part of the protocol. It knows how to take that input, put it in the stack. Else, what is else? It means that parentheses of position index is not an opening parentheses. Well then, I will check if S, my stack, is empty. What is else? Else means it's not an opening parentheses, it means it's a closing parentheses. So if it's a closing parentheses, I should have opened it before. And if my stack is empty, aha, that means I didn't store it in my stack, it means I didn't have an opening parentheses. So in that case, I will immediately make balanced to false. That will allow me to get out of this loop. Otherwise, here, else means that the stack is not empty. There is something in there. And now I'm dealing with a character that is a closing parentheses. Well, what do I have to do? I will pop it. Pop what? I will pop the last character that I added in my stack. And I will put it in top. So top is a variable that references the last character that I added in my stack. And I add in my stack, remember I push only those opening parentheses. So on one hand, I have the parentheses at position index that is not opening, so it must be a closing. And on the other hand, I'm popping from the stack the last one that I added, and I have to compare them. So if top and parentheses at position index do not match, then balance is false. What does it mean, do not match? Well, it means that one is a curly bracket, the other one is a square bracket. One is a parentheses, the other one is a square bracket, and things like that. They do not match. They have to be both from the same family. And if, this is the end of this if, and this is the end of this if. So I dealt with the case of an opening parentheses, I dealt with the case of a closing parentheses. I dealt with the case that I have a closing parentheses but I don't have an equivalent opening, and I dealt with the case where they do not match. Otherwise everything is fine, and I increase my index by 1. I move to the next character. And then it goes back to the beginning of the loop and I test, is it balanced or not? Did I reach the end of my parentheses? If not, I'll do it again. Otherwise, I will leave and I check if it is balanced. Well, everything is balanced that I've seen, but what do I have in my stack? If the stack S is empty, that's fine. Everything is fine. I finished and it's balanced, so I return true. Otherwise, there's a problem. Either it's not balanced or the stack still has something. What does it mean that the stack still has something? Well, I pushed it in the stack. When? When I had an opening parentheses. I had an opening parentheses that I never popped. Therefore, I open a parentheses that I never closed. So I have to return false. So that's my algorithm. I'll leave you a few seconds looking at it again. As I said, this is an algorithm. It's not in Python. I have to write it in Python. Converting into Python is not difficult, actually. It's so well detailed here in different steps that make sense. I can write it like this. Okay, so here's my function. Let's call it par checker. And par checker receives as a parameter symbol string. So symbol string is the input. It's the equivalent to parentheses here. Create stack. Well, I take a variable called s and I assign to it stack. So that will initialize the constructor that will create an instance of the class stack. That instance of the class stack knows all the protocol that we defined, that interface. It knows push, it knows pop, it knows seek. And then I have balanced is initialized to true. I have index, which is initialized to 0. And then while the index is smaller than the length of symbol string, this is equivalent to that, and it's balanced, so exactly the same as this conjunction, okay? What do I do? Well, I have to check if that symbol at position index is in the set of opening parentheses. Well, because I'm using parentheses of index many places, I will just copy it into a variable called symbol. So symbol is assigned symbol string of index. Then I compare. If symbol is in the set of opening parentheses, then what do? I push the symbol where in S. So I will call S, invoke the method push, and I give it the symbol. Done. Then I have to check if the stack S is empty. Well, I say, hey, S is empty. I invoke the method is empty of S. S is a stack, and it knows is empty. It knows push. It's part of its protocol that we defined in that ADT and that we implemented in our class. Okay, so if the stack is empty, I just do the same thing as here. Balanced is assigned false. Else, well, I'll ask S pop, like I did here, and then I assign it to top. If not matches top and symbol, if these two do not match, they're not from the same family, curly bracket or square bracket or parentheses, then balance is false. Exactly like here. You see how easy it is once you write it as an algorithm. It's straightforward to make it into Python. And then I have index is assigned index plus 1, and I finished my loop, and at the end they'll say if it's balanced and the stack is empty. How do I know the stack is empty? I'll ask it, hey stack S is empty. I invoke the method, then I return true, otherwise I return false. That's it. Well, there's something missing. Matches. Matches is not a known command or function in Python. It's a function that I called, but it doesn't exist. I have to create it. I have to define it. What does matches do? It receives two characters, top and symbol. Top and symbol. Top that I popped from the stack, so it's in opening parentheses, and symbol is the current symbol, which is, since I'm in here, it means it's actually closing. So I get an opening character for an opening parentheses of one sort, and a character for closing parentheses of one sort. I don't know if it's a curly bracket or square bracket or whatever. And I need to know if they're from the same family. So the input are two characters. The output is either true or false, because I'm using it in a Boolean expression here. Okay, so here's a new problem. I have an input, which are two characters, and an output, which is a Boolean. How do I define it? Well, relatively easy. So this is my method called matches. I get two characters, let's call them open and close. Okay, and I want open and close to belong to the same family. So let's define these family. I have a string called opens. It's different than open, there's an S here. Opens, it's just string parentheses, square bracket, curly bracket. And closers are the same, in the same order, but closing parentheses, closing square bracket, closing curly bracket. They will match if the index of open inside opens is the same as the index of close in closers. Well, that's what I write. So if index of open in opens is equal to index of close in closers, then I return true. Otherwise, I return false. Okay. Just a small interruption here. I'm making an assumption that open and close will belong to these sets. Okay. Normally, I have no idea how somebody will call me matches. So I should verify that my input is correct. I should do a validation of that input. If it's not in these sets, I should say, oops, stop. This is what we call an exception. So if I find an exception, I'll stop and I raise an exception. Okay? We will see that in the next chapter. But here we assume that the data is correct. Open and close are an opening parentheses and close is a closing parentheses. But remember this example when we get back to we'll talk about exceptions. Now, let's try this par checker. So I have parentheses here, and I verify that they are correct. And if I call par checker, it should tell me everything is correct, and indeed print par checker of these parentheses, it returns true. Now I give it new parentheses where I on purpose make mistakes. So you can see here I have a square bracket that is opening, and I have another square bracket that is opening, and I never close it. Okay, and same thing here, I have a closing parentheses that I never opened, and another one closing parentheses. So there are mistakes here. And if I call par checker with these parentheses and I print, it'll say false. So it seems to work. And the beauty of this is I was able to solve this problem of checking the parentheses thanks to the new tool called Stack. Thank you, Stack. So this shows you that once you build this class, you can use it. You can use it. It becomes a data structure like you have lists, like you have sets, like you have dictionaries. Now you have stacks that you can use. Let's test it and see how fast is it, just for fun. So we'll test it with, let's say, 10 times, calling 10 times for a particular long string of parentheses, and then we'll call it 100 times for the same, and we'll see how much time it takes. So this is what we'll do. We'll call par checker 10 times and 100 times, and the 100 times we'll do it actually 3 repetitions with a long sequence of parentheses. Okay, so we defined P is this string, and then we will call par checker with P as a parameter to timer of time it. We create a timer here T. Par checker will import it from the main, and here I'm printing the time it takes to time T 10 times, and then I will do it the same thing. I'll say, hey, T is this timer, repeat 3 times, 100 times. So it'll return here, in this case, it'll return the time for 10 trials. Here it repeats 3 times, 100 trials. And this is what you get. So for 10 times, you get 0.001 milliseconds. But when I do it 100 times, I get a list of 3 possibilities. The first is, because I'm doing it 3 times, 3 repetitions. The first repetition is 0.01. So indeed, it's 10 times slower. And here is 0.01, 0.01. So yeah, it seems to behave as I expected if I do 10 times more than this time. So obviously, it is 10 times slower. Okay. But when I think about how I implemented the stack, I piggybacked on the list because Python gives me the list, and I made the decision to put the top of my stack at position 0. Is it a good idea? Is it smart? When you think about it, whenever I push an element in that stack, I will put it in position 0 because that's where the top is, and I push at the top. But if an element is already at position 0, it'll be pushed to position 1 to make room for this new that I'm pushing in. And if I'm pushing somebody in position 1 and there's somebody else in position 1, I have to push it in position 2. And if position 2 is taken, I have to push it in position 3. So that means each time I push an element in my stack, I may have to shift many elements. Not a good idea, is it? I thought it's just a push and it's done, but it appears that I have many basic operations to do each time I do a push. How many operations? Well, as many as I already have elements in my stack. What about the pop? I pop at position 0 because that, again, is the position where I decided to have the top. If I pop at position 0, well, position 0 now is empty. It'll be taken by position 1. And position 1 is empty, so it'll be taken by position 2, the element in position 2. And same thing, I'll have to shift again. So each time I push, I have to shift to the right, and each time I pop, I have to shift to the left. So this push and pop is making these elements in the stack, in the list, simulating the stack, dance from left to right. That's not good. So what's the solution? Well, the solution is to re-implement my stack, again using the lists, but I will change the choice where I put the top. Instead of putting the top at position 0, I'll put the top at position n. The last element is the top. What's the advantage? Well, each time I'll push, I will just append at the end. I don't have to shift anybody. And when I pop at the end. I don't have to move the others either. That seems to be faster, doesn't it? Well, let's implement it. How do I implement it? I have to rewrite the methods that are in my protocol, in my interface. Okay? So that means the init. That means the init is the constructor in the class. I have to rebuild the class. I have to rebuild the push, the pop, the seek, the peak, sorry, and the is empty, the size, and so forth. So let's write them. Well, the init, the constructor, is the same. I'm using a list. So in the beginning, the list is empty. So the items of self is an empty list. But for the push, when I give it an item, I will ask items to append the item at the end. The items of self. While for the pop, I will use pop of list because items is a list and list knows pop, which means take the last one at the end, and I will return that. Notice that this pop that I'm invoking with items is the pop for the lists, while this pop that I'm trying to define is the pop for stacks. These are the same kind of names for two methods, one belonging to the lists that is already built in Python, and the other one belongs to the stacks that I am defining right now. So it's like two different languages. One is for the language of the lists, one is for the languages of stack. One is in French, one is in English, but it happens to be the same word. Okay? You have to be very careful. I'm invoking pop here with items, which is a list. Items of self, okay, which is a list as you see here. Now peak. What do I do with peak? Well, peak, I'm supposed to look at the last element because that's where the top is. Well, length of items of self minus 1 is the last index. And then I take that of items, self, and I return it. That's it. So I return a copy of what exists in the last element. Is empty? Same thing as before. I check if items is equal to the empty list. And size, I will call the length of items of self and return that. So if I put the two implementations side by side, what do I get? I get this. This is the case where before, in implementation 1, we said the top is at position 0. And this is where we said, no, the top is at position n, the last element. Well, look at the code side by side. And what you see here, the red, are the differences. Instead of inserting at position 0, I append at the end. Instead of popping at position 0, I pop from the end. Instead of peaking at position 0, I peak at the last position. That's the only difference. Okay, so what we'll do, we'll scrap implementation 1, replace it with implementation 2, and let's use it. But before we use it, we have to test it. Even though you look at this, say, these are easy, let's use it. No. Whenever you make changes in a class, you need to test it again in isolation. Well, luckily we had the program that we used to test our first implementation. Let's test the second implementation the same way. So I create a stack from the second implementation. I ask show, I check if it's empty, I push Bob, and I look at the results here. It shows me that it is behaving as I intended it to behave. Okay, when I start in the beginning, it's empty, and yeah, it shows me that it's empty. When I add Bob, I can see Bob, and it's not empty anymore. When I add Eva and Paul, I can see them in order. Ooh, look at that. The end is the top, and indeed, Bob was added in the beginning, and then I have Eva, then I have Paul. So my top is at the end. It's reverse of before, of implementation 1. But the size works. When I pop, you see, when I peek here, it didn't return Bob. It peaks at the right place, Paul. And says Paul is on top of this list. So it seems to work as I intended it to do, because when I pop here, the item, it's Paul that is popped. So it is popping from the end, which is the top. So I'm happy with this. It seems to work like implementation 1. Let's time it and compare it with the first implementation. And you can see that, yes, there is a difference between the, so I also did it 10 times and 3 times, 100 times. And you can see that the second implementation is faster than the first implementation. And this is due to the fact that I don't have to shift left and right the elements in my stack each time I pop in and push. But here's the beauty of this whole lecture. This is the message that you need to keep in mind. Because of this isolation, remember we talked about encapsulation and hiding the data, because I implemented my ADT separated from any other code that is using this data structure. So I created a class by itself, and then another code is using that class. If I change the class, as long as I don't change the interface, how to talk to these instances, my code that is using that class doesn't have to change at all. So what happens here, I had a class stack where I implemented this behavior, all the different methods, and then I made changes in my properties, their private properties, and because of that I had to change my implementation of the different methods. Well, just by scrapping the old implementation and keeping the new implementation, because I didn't change the public interface, how the outside world can see it, well, part checker can still use it without changing the code of part checker whatsoever. Okay, so I just import the new stack and the code doesn't change at all. The only impact is that it'll be faster, but there's no impact on the code itself. I don't have to change lines of code or anything. Okay, so now that we have the stack and we used it, we are happy with the second implementation. We'll scrap the first implementation, we'll keep the second implementation. Is it only useful for part checker? No. We'll use it for other problems, not just checking parentheses. Now that we have this tool, it's in our toolbox, we can use it for other problems. So let's see another problem. I'll talk about arithmetic expressions. So instead of just having parentheses, let's have operators inside and operands as well, and we can try to evaluate these expressions. So in arithmetic expressions, we have operators like plus and minus, division, multiplication. Each operator has 2 operands. So a plus b, a and b, they're 2. You can say a divided by b, the 2, a multiplied by b, or a minus b. Then expression, we can have many operators, not just one, okay? And we know that operators have different priorities. So, for example, the multiplication and the division, they take precedence over the addition and the subtraction. So, the way you typically write an expression is in a particular notation that we call the infix notation. What is the infix notation? Infix, it means that the operator is inside and between those two operands. Okay, like you say, x multiplied by w, or x multiplied by y. So x multiplied by y, you have x multiply y. The two operands are in between the operator which is in the middle. And that's how we write it. And because that's how conventionally we write it, it may create some ambiguity. Because if you write x multiplied by y plus z, well, because of the precedence, it's equivalent of putting parentheses between the x multiplied by y, saying do that before you add the z, because the multiplication comes first. Okay, and indeed, if I put parentheses somewhere else, I add the y plus z, then I multiply by x. It's equivalent to putting these parentheses. So, in order to remove the ambiguity, we should always put parentheses to know which one we do first. Okay. How do we remove this ambiguity to the computer if we give expressions to evaluate? Should we have parentheses everywhere? It's complicated. So this is where the other notations come in this picture. There are other notations, not just the infix. There's the prefix and the postfix expressions that actually don't need parentheses whatsoever. The parentheses are only needed because of the infix being ambiguous. So I'll show you what is this prefix and postfix notation. The infix is when the operator is in between the two operands. The prefix is when the operator is before the two operands. Like multiply xy means take xy and you multiply by each other. The postfix, post means after. The operator is after those two operands. So you say xy multiply. It means that you multiply x and y. So pre is before, post is after, and in is inside. So infix, prefix, and postfix. Easy to remember. Okay. So let's see examples to illustrate the fact that actually you don't need these parentheses to disambiguate. The prefix and postfix are not ambiguous whatsoever. So here's an example. We started with x plus y multiplied by z. Well, in the prefix notation, you write plus x multiply yz. The multiply is before the y and z, means these two, you multiply them together. And then the result and the x, well, they're added. Okay? So in the postfix, the operator comes after. So I have x and y, but I still don't have an operator, z. Multiply. So the multiply applies to the y and z, and then the plus applies to the result here and x. Okay. So if you want to put parentheses to say no, I want the x and y to be added up first, and then I multiply by z. Well, this is how you write it in the prefix. It's multiply plus x, y, z. Why is that? Well, because the plus applies to the x and y immediately after. This gives you something that you can multiply with a z. And here you can see that, I have a plus. It means the two before it, two operand before it have to be added. And then I have a z, and then I have multiplication. Multiplication is z and the result of this operation. Okay, so that's exactly what we do here. We add x and y, add x and y, add x and y, and then I multiply by z, multiply by z, and then here multiply by z. Here's another one a little bit more complicated. You see I'm adding x and y, that's why they're in the between parentheses, then I'll multiply by z, and then at the end I add v. Well, in the prefix, it's very easy. This is how you write it. It's plus, multiply plus, x, y, z, v. Why is that? Well, because you come here, you find, oh, I have an operator. The operator applies to x and y. Okay, I'll actually use the pen to better see it. So the plus here applies to these two. Okay, and then the multiply applies to these two, the z and the result, and then the plus applies to v and the result. Okay, and then in this case, in the postfix, you see I have x plus y. Indeed, I have a plus. I take the 2 before it. Okay, and then I have a multiplication. It's z and the result. Indeed, like here. And then it's only at the end I have the plus, and I add v with the result. Okay, so it works without any parentheses. I don't need any parentheses to make it work. Why is this interesting? Well, it's interesting because if I just focus on postfix expressions, suppose I had postfix expressions, I can easily, using a stack, calculate the result. Very easily. How? Well, if I have a stack here, I will traverse this string and I'll say x, oh, I don't know what it is. I'll put it in the stack. I'll push it in the stack. And then I come here, y, what is it? I don't know what it is. I just push it in the stack because they are operands. I push them in the stack. Then I find an operator, plus. Oh, what do? Plus is an operator. It needs 2 operand. I will pop 2 operand from my stack, apply the operator, so the plus, and then x plus y, I will push it in the stack. And then I'll find another z, I will push it in the stack. This is an operator, multiplication. I will pop 2 of them, one is z, and pop the other one, which is x plus y, and I'll multiply them together and push it back in the stack. And then I find v, I'll push it in the stack. I'll find plus, I will pop 2, I'll add them up, push them in the stack, I have the result. A little bit confusing? Well, let's see a real example. So I have 32, 5, plus 2, multiply. What is that? Well, difficult to calculate. We are used to infix, we are not used to postfix, but look at how easy and elegant it is to calculate this using a stack. I have a stack, I traverse this, I have 32. What is it? It's an operand. I'll just push it in the stack. Okay, then I move to the next one. It's 5. What is it? It's an operand. Push it in the stack. And then I have an operator. Plus, I will pop 2 element, the 5 and the 32, and apply the plus. So the 5 and the 32, and that becomes 37. I push it in the stack. Then I go to the next one, 2. Oh, 2 is an operand. So I push it in the stack. And then move forward, I have a multiplication. So I'll pop 2 from the stack, the 2 and the 37, and I'll multiply basically 37 by 2. And that gives me 74. Et voila. So what's the result? The result is in the stack, at the top of the stack. So in the infix notation, it looks something like this. It's 32 plus 5, okay, multiplied by 2. It's indeed 74. If you're not convinced, let's take another expression. This expression, 2, 3 plus 5 multiply, 3, 7 multiply, plus 2 minus 4 divide. What is that? Well, that's a postfix expression of this expression in infix. This is infix notation that you are used to. So 2 plus 3 multiplied by 5 plus 3 multiplied by 7 minus 2, the whole thing divided by 4. I know the precedence of the multiplication, so obviously I need to multiply 3 by 7 first before adding them up, and I need to multiply the 5 by this result before I add them up. So let's make it like this, showing 2 plus 3 is actually 5, and 3 times 7 is 21. Then 5 times 5 is 25. This 21 minus 2 is 19. 25 plus 19 is 44 divided by 4. That gives me 11. So this should give me 11 as a result. Okay? Let's see how we can solve it very easily using a stack. Using a stack and blindly. What is blindly? Each time I find an operand, push it in the stack. Each time I find an operator, I pull 2, pop 2 from the stack, apply the operation, push them back in the stack. Keep on doing that, blindly. At the end, the result is at the top of the stack. Let's see. So I take 2. What do I do with 2? With my stack? Well, the 2 will go on top of the stack. Okay? Now move forward. 3. What do I do with 3? Push it in the stack. Now I move forward. What do I have? Plus. Plus means I pop 2 from the stack, add them up, because it's an addition, and I get a 5, and I'll push it in the stack. Move forward. I have a 5. What do I do? It's an operand. Just push it in the stack. Oh, multiplication. What I have to do is pop 2, apply, put it back in the stack. So I pop 2, 5 and 5, multiply by 5 by 5, get 25, push it in the stack. Okay? Then I move forward. 3, push it in the stack. 7, push it in the stack. Multiplication. Oh, I pop 2, multiply them, and push it in the stack. 21. Oh, I have a plus. I have to add them up. 21. I pop them up, pop them out of the stack. 21 plus 25. That's 46. Ooh. And then I have a 2. I just push it in the stack. A minus. What do? Pop them from the stack, apply, and then push them back in the stack. So 46 and 2, and I do a minus, it becomes 44. Then I have a 4. What do? Push in the stack. Simple. Blindly. I have a division. Division, it's an operator. Pop 2 from the stack, apply it. Becomes 11. What's the result? At the top of the stack, it's 11. Exactly what I expected. So you see, using a stack, it becomes easy. So since we know that given a postfix notation, I can evaluate the result using a stack, it would be interesting if I'm given an infix notation to do the same thing. So what I'll do, I'll take the infix notation, I transform it into postfix notation, then use this algorithm, and voila, I get the result. The question is, that's a different problem. How do I get from an infix notation to a postfix notation? We will see that we can also use a stack to solve that particular problem. It's a different problem, but I use a stack and again use a strategy with the stack to blindly convert an infix notation to a postfix notation. Once I have it in a postfix notation, I'll use a stack again with a different strategy like I just showed you now, and we'll evaluate the result. So this is what we will evaluate the expression to get the result. So this is what we will see next time. And yeah, you can practice with a stack and some expressions like that. It's a lot of fun. You'll understand better if you, again, you put your hands in the dough and you get your hands dirty. When we'll meet next time, you'll have a better understanding of the algorithm we are doing. Okay, so see you next time. Stop recording.